Hello, welcome to this lesson. In this video, we're going to learn about the phase relationship between current and voltage in a pure inductor circuit. So, in this case, we are dealing with alternating current. Okay, so we have an alternating voltage source here, which means that we're going to have an AC current in the circuit. So we have an inductor here. So what this inductor does is that it stores electrical energy in its magnetic field when current passes through it. So we're going to look at the phase relationship between current and voltage in this circuit. So the voltage is given to us as V equals Vm sine omega t. Okay, so this is the voltage at a particular time t. Okay, and then the Vm is the peak voltage. So what will happen is that because of this alternating voltage, there will be an alternating current passing through the inductor, and this current will induce an EMF into the inductor. Okay, and this EMF is given as E because minus L di dt. Okay, so what will happen is that since the only element in this circuit is the inductor, the voltage from the voltage source will be equal to the voltage across the inductor, and this voltage across the inductor is the EMF E here. But the only difference is that the EMF on the inductor will be opposite to the total voltage. Okay, so I'm going to have V equals minus E. So what I'll do is that I will substitute the value of E here, okay, into this new equation that we have. Okay, so when I do this, I'm going to have V equals minus E. Okay, E is minus already, so I'm going to have minus, then minus L di dt. Okay, this is what we are going to have. So when we do this, we are going to have V equals L di dt. Okay, but you know the actual value of V. Okay, so let's do the substitution. So you're going to have this to be Vm sine omega t equals L di dt. Okay, so this is what you have now. Okay, so what I'll do is that I'll group the like terms here. Okay, so you have t here, you have the t here. So I'm going to group these two so that the di2 can be on its own. The Vm and then the L are constant, so you can also put them on any of the side, whether the left hand side or the right hand side. So when I do this arrangement, you're going to have the I, okay, to be equal to Vm over L sine omega t dt. Okay, this is what you are going to have. So what you do next is that you are going to integrate this expression. Okay, so when I integrate this, the I, we are going to get I, which is the alternating current. Okay, this will be equal to, so you see that the Vm over L will be a constant, so you can bring it behind the integral symbol. So and then you are going to have Vm over L. Okay, they are constant. So the main focus will be on the sine omega t since it has the variable there. So we're going to integrate sine omega t. When I do this, you're going to get minus cos omega t over omega. Okay, this is what you're going to get. And then let's bring the constant of integration, which is c. So I'm going to rewrite this as I equals minus Vm over L, okay, and then the omega. So let me bring here omega L cosine of omega t. Okay, this is what you're going to have plus c. But what will happen is that the voltage is time dependent, which means that the current will also be time dependent. But looking at this terms that we have here, we have the variable t here, but we don't have the variable t here. So for that reason, we can make the constant 0 since it is not time dependent. So at the end, you are going to have the current I to be equal to minus Vm over omega L multiplying cosine of omega t. Okay, so now this is the expression we have for the current. Okay, but you see, we can't compare this to the voltage because the voltage is given in terms of sine omega t, and then we have cos omega t here. So we can't actually compare the two to see the phase difference. So the best way to do this is to change this expression here, okay, to a sine expression. Okay, so let's look at how you are going to do this. Okay, so at this point, you are going to use a trig identity here. Okay, so that would be cosine of omega t, okay, will be equal to sine of pi on 2 minus omega t. Okay, this is the identity that we are going to be using. Okay, so you are going to use sine pi on 2 minus omega t instead of cosine of omega t. So you are going to have the expression I equals minus Vm over omega L multiplying sine of pi on 2 minus omega t. Okay, so now when you look at what you have here, still we can't compare it to the expression for the voltage because when you consider the expression for the voltage, the omega t there is positive, but the omega t here is what? Is negative, so we still can't compare this. So for this to be possible, we are going to use another trig identity. Okay, so let's look at that one also. So that will be the identity sine of sine of minus x will be equal to minus sine x. Okay, so let's look at how you're going to apply this identity here. Okay, so basically I will write this expression as I equals I'll assume that the negative is attached to the sign. Okay, so what you do is that you are going to distribute this negative here to the terms in the bracket. So let me write this way. So we have something like this: minus sine of pi on 2 minus omega t. Okay, this is what we have. Okay, let me write this on the right hand side. So we have something like this: minus sine of pi on 2 minus omega t. Okay, but we want to take the negative sign inside. Okay, so when you do this, you are going to have sine of so let's distribute it. When you do this, you are going to have minus pi on 2 plus omega t. So now you have the omega t to be positive. So we now have the I to be equal to Vm over omega L multiplying sine of omega t plus, sorry, it is minus rather, minus pi on 2. So this is the expression for the current. So when you compare this current expression to the voltage expression, you see that the current is um, lagging the voltage by 90 degrees, which is the pi on 2. Okay, so that is why you see in books that saying that in a pure inductor circuit, the current lags the voltage by 90 degrees or by pi on 2. This is the reason. So that would be the phase difference between voltage and current in a pure inductor circuit. Okay, so now let's look at something here. So this expression that I have there is known as the inductive reactance. Okay, and then it is represented with XL, which is equal to omega L. Okay, So you can write the expression for the current as I equals the peak voltage over the inductive reactance multiplying sine omega t minus pi on 2. Okay, so this is what we have now. Okay, so this term here or this expression here, okay, actually represents the peak current. Okay, so that's Im is equal to Vn over the inductive reactance. So what this actually means is that if if sine omega t minus pi on 2 is equal to 1, then you are going to get the current I to be equal to the peak current. Okay, that's if only the sine omega t minus pi on 2 is equal to 1. So now that you know that Vm over xl is equal to Im, we can substitute that into this in place of what you have there. So you're going to have I to be equal to Im sine omega t minus pi on 2. Okay, so you see that with this expression here, we can actually do the comparison in a simple way. Okay, so we have the current here, and then write the given voltage expression too, which is Vm sine omega t. Okay, no, I don't even bracket omega t. So you see that the current lags the voltage by pi on 2, which is the same as 90 degrees. So the current is actually lagging the voltage, okay, by an angle of what, 90 degrees. So let's look at what this actually means. So I have this figure here. Okay, let me zoom it. So this figure here actually shows the phase relationship between the voltage and the current. Okay, so I have here the voltage. Let me change the ink color. So I have here the voltage, okay, and then this is the current. So you can see that the current is actually lagging the voltage, okay, by pi on 2, which means that on this diagram here, okay, if you are to start reading, the voltage will start um okay, let's say the voltage wave will start first, and then after an angle of 90 degrees, then the current wave will also start. So you could see that the current actually delayed by some angle, which is 90 degrees. So this is the phase relationship between voltage and current in a pure inductor circuit. Thank you very much for watching this video. Please make sure you like the video and subscribe to the channel.